I'm Ryan Russell again, and this time I brought Nicolas Brulez with me. Did I pronounce your name correctly?
Yeah.
Okay. And we're going to show you how to do some malicious code analysis, specifically with a time constraint. And that doesn't just mean that we don't have enough time to present fully today. We're actually talking about when you're looking at the malicious code. So, quick poll, which will help direct my talk a little bit. How many IDA-Pro users in the room? Okay. Not as many as I would have thought. Okay. Thank you. I'm trying to go through the slides a little bit quickly. Hugo's gone ahead and given us permission to go ahead and make you late for lunch. So, no pressure there. At the same time, I'm going to try and keep my English speaking speed to a low level so that, as Nicolas has reminded me, there's several major analysis methods you might use when you're looking at a piece of malicious code. In our case today, we're focusing on Windows, pretty much strictly because if you're interested in malicious code, that's where the vast majority of your samples are going to be functioning. So some of the major analysis methods are using the sacrificial lamb, and by that I mean something in particular, a box that you're willing to infect. Oftentimes VMware or virtual PC. If you work for an actual real antivirus company, they're very, very strict about the boxes that they use for research. They're on a disconnected network, different room. Supposedly some of them are in a Faraday cage and all this other kind of fun stuff. I don't think any of them have the poisonous gas rooms or anything yet. The nice thing about sacrificial lamb is that can be a big time saver. Later on in the talk, we're going to talk about things like unpackers and ways to find out where a piece of malicious code talks in the network. If you have a box that you're willing to infect and you're interested in some very particular pieces, that can sometimes give you a very quick answer. It's like, well, maybe I'm not going to bother figuring out how the file dumper works. I'm actually just going to infect a box and grab the files off the disk when it's done. I don't necessarily want to disassemble the network piece. I'm just actually going to sniff it out after I infect a box and maybe let it talk on the network. You're going to see myself and Nicolas do a little bit of risky behavior in terms of how we're analyzing stuff. This is my don't try this at home warning. Because when you're doing a debugging of a piece of malicious code, obviously there's a chance you'll infect yourself. Other ways of determining what a piece of malicious code does, and again, this is when you're running on a box that you don't necessarily care about. You can restore back to a known state. If you're running it on a sacrificial lamb, you might use some tools like FileMon and REcon from the sysinternals site. Those are tools that will tell you every registry access, every file access that a particular process is doing. Same thing with Ethereal to monitor the network. The one we're actually going to be demonstrating today, of course, is disassembly with some light debugging. Oftentimes you're going to need to use a debugger in conjunction with a disassembler in order to get through some of the difficult pieces of code. And then finally, Nico reminded me that the Halvar's BinDiff program, it's a commercial tool, has a feature I didn't realize that he'd added in there, which is you can actually, not only will it tell you the differences between two binaries, for example, the .a version of a worm and the .b version of a worm, which are going to be slightly different, and it will give you a dump of what the differences are between the two. But also will actually let you take all of the imports from the .a version, all of the names and things that you did in IDA-Pro manually, and automatically port those over to the matching functions in the .b version, which is something I didn't realize, and that actually can be a huge time saver if you've been following a family of virus or worm. So we're going to focus on disassembly specifically today. Reasons for that are it gives you the most complete picture. You can go ahead and run a piece of malicious code on a sacrificial lamb and observe the external behaviors, but of course you're not necessarily going to see everything. You'll find that some sites that it tries to talk to are down and don't exist yet. You'll find that they do things on different days of the month. Code Red, you may recall, did things depending on what day of the month it was. Sometimes it would spread, sometimes it would DOS the site, and sometimes it would just go idle. Which, funny story, bit me really hard when I was trying to do a demo based around Code Red, and I managed to, after working all week, managed to do my demo on the day where it just sits there idle. Other reasons you want to have a good disassembly is that you can reuse code fragments, meaning you can actually take pieces out of the malicious code. Maybe there's a particular function that does some encryption or decryption, does some communication routine, and if necessary, once you've disassembled and identified those pieces, you can pull them out and replicate them if there's a need to do that. I usually find there's not, but occasionally I've had a need to pull a piece out and want to run it outside of the program. You can also, if you have a need to, and hopefully most of the time you won't, you can actually make modifications to a piece of malicious code in order to use it for research purposes. I've done this a couple times where I've taken a worm and I've partially neutered it in order to make it a little bit safer to work with, or so that I could run one piece of it and not have the rest of the code infecting the box, or that sort of thing. So hopefully most of the time you won't have to do these. One problem with disassembly is oftentimes it's the slowest method to get a particular answer, but it is the most complete. There's a particular purpose to the disassembly, and this is understanding. And for a piece of malicious code, that's probably just about the only reason you'll be looking at it. You want to know what it does. You're not actually trying to run it, for example. You're trying to get the binary into your head. You're trying to install this worm into your brain so you have some ideas how it works. If you work for a company that does reports or that sort of thing, you're trying to get this thing in your head so that you can later go back and do a report on it or hand it off to the guys who want to write a disinfector, or you want to be able to write some tools that can spot and identify maybe some IDS signatures. Most of the time, you're not trying to modify the binary, find a vulnerability in it, or fix it and improve it. This is a little bit different from a number of the other types of reverse engineering you might do. This is, some of this has been talked about. Some of this is something else you might do with REcon, for example. If you're trying to crack a protection scheme or some other sort of protection on a program, typically you're going to be modifying the binary as your end result. We're not trying to do that with the worms usually. For vulnerability research, you're trying to find particular function calls in a program, trying to check buffer sizes, all those sorts of things you would do to find a vulnerability in a program. We're not trying to usually do that with the worm. Although there have occasionally been some interesting buffer overflows in the worms, and there's been at least one other worm that took advantage of an overflow in an FTP server of a previous worm. You're not trying to debug the malicious code. You're not trying to make it work better. To give you an example, in the NIMDA worms from a couple years back, there was a routine in it where it would go through and infect a bunch of files, or look for a bunch of files, drop itself, that sort of thing. The same routine was used to go through and delete everything on your hard drive. You may recall that NIMDA never actually did that. That's because there was a flag that was set that said, just don't do this. I guess the virus author got a little nervous, left that particular feature off. We're not necessarily trying to debug it and fix it and turn that feature back on. We're not trying to usually, for a piece of malicious code, analyze it for the purposes of pulling out interesting algorithms. We're not trying to reverse engineer it so that we can interoperate with it properly. We're not trying to figure out, the neat little algorithms that it does, and so that we can steal those and use them in our own program. And these are some of the reasons why malicious code analysis is easy. And I say easy, it's a relative term. Easier than, for example, reverse engineering a Nintendo DS and getting Linux to run on it. We don't need to patch the binaries typically. We already know some of what it does. This is an important feature. You have a suspicion or a knowledge that this piece of code you're looking at has particular characteristics. You know it's a piece of malicious code or have a strong suspicion that it is. And oftentimes, the way you got it tells you an awful lot about how it works already. For example, if you're aware there's a worm out there and you set up a little honeypot to grab a copy so you can analyze it, you already know quite a bit about that worm. You know how it spreads, some of the services it hits, what port numbers it uses, that sort of thing. So we can make some big sweeping assumptions a lot of the time with malicious code. And this means that when we're looking through sections of the binary, we can say, oh, okay, I can see this routine looks like it's a mailer, an SMTP client. And so I'm going to assume that a lot of the code below it is related to that. I'm just going to tag the top level piece and only come back to it later if I need to, or if I'm interested in that piece. Most of what I'm here to show today is how I actually use IDAPRO mostly. I think you'll find that IDAPRO is a more or less standard tool. People trade IDB files like they would Word document files. This is fairly common, and so every antivirus company that I've ever traded a sample with, it's generally done as an IDB file, or there's one that goes with it. A lot of people don't necessarily like this. IDAPRO is a commercial tool. It's fairly expensive. It's actually somewhat difficult for individuals to buy sometimes. The data rescue guys are very paranoid about piracy. They won't sell to people in Russia, for example, they claim, because it's a complete country of filthy pirates. I tease them a little bit. I do feel bad for them, though. What they've done is they've got a commercial tool that's fairly expensive that they sell, that every single cracker in the world wants a copy of. So they're not in a great position, but it is a really good tool. So if you've got a means or reason to buy it, I recommend it. The keys to using IDAPRO effectively or quickly are to identify the sections of code that give you the biggest impact. For example, the library functions, the imports. You want to make sure you have all those well identified, because those are going to be called hundreds and hundreds of times by other pieces of the program. And you'll find that having a library named, if you can see that it's a string copy or a string cat, that immediately gives you huge clues as to what this piece of code is doing. Start with the most commonly used pieces if possible, meaning that if you've got a function that you don't know what it is yet, but it's at the bottom of the call trace and there's 100 other functions calling it, it's probably worth your time somewhat early in the process to figure out what that function does, so that you can name it, identify it, and that'll be tagged everywhere else in the program. And then the last point, and this is one I typically get sidetracked by, stick to the program flow you need to know about. Decide on a goal ahead of time when you're looking at it. Pick a piece that you want to look at, because it's easy to go off on a sidetrack and realize 3 hours later, oh yeah, I was looking at the network piece and I'm off somewhere here in the IRC client. Priorities, as I mentioned, are the library functions. This is most programs that are compiled with a normal C compiler include pieces of libc in with the code, so that your string copy, all your string functions, memcopy, all these other little library pieces are actually live with your binary and travel around with it. So it's important to have those identified. The imports, these are, and again, this is for any kind of a system that supports dynamic library linking. It's going to be reading in a set of libraries at load time and possibly at runtime as well. There's a set of functions in Windows to dynamically load up libraries under program control, and that's another piece you'll want to take a look and identify. The entry points, and I'm going to show an example here in a moment where the entry point is not obvious. There is a tagged entry point. This is the Windows itself needs to know where do I start the code at. However, that's not useful to us, as I'll show in a minute. And then we want to look at any particular interesting calls. And this is a little bit of this is experience, a little bit of it's obvious. Some of the interesting calls are things like load library. I mentioned that Windows can load up libraries at runtime. Some malicious code is designed to have as very few imports as possible at the actual load time, and then they manually load the rest they need later on. So sometimes that's very important. Depending on what kind of pieces you're interested in the malicious code, you want to look at the network calls, RAND. If you've got a worm that's got a particular spreading algorithm, that's one of the pieces that people are often very interested in. The RAND function is typically going to be involved. You want to look at where it's writing to the registry or the file system, and you want to look at things like create thread. A lot of malicious code will fire off worker threads, and IDAPRO doesn't count that as a branch, so that's something you want to manually take a look at and mark. So when you're looking at a call flow diagram that IDA does, and you'll see a few in a bit, it doesn't include things like create thread. It doesn't count that as until it's branch construction. And then finally, somewhere towards the end, you want to do some structure cleanup, meaning that, again, as I'll show a couple of examples here, IDAPRO is not perfect. It doesn't tag everything properly. It misinterprets some things, so oftentimes you'll have to go back and mark something as a function, mark something as a string, and it's a bunch of cleanup work. Some of this is valuable sometimes for filling in other parts of the program. So I'm going to do a demo, and this is a Trojan called Hot World. Actually, we've got 2 Trojans to demo today. It's just coincidence that the 2 things I picked ended up being Trojans. This is the Trojan that was recently in the news for having been found in use in Israel in a bunch of, I guess, industrial espionage cases. So this is a sample I was provided, and I'm going to take a brief look at it. Now this thing, as you'll see, is actually huge. It's 500K. This is about, and most of its code, this is about 10 times larger than your typical piece of malicious code that we'd be looking at. I'm going to go through it extremely quickly because it's massive, and I can't possibly have enough time to show you everything that I would like to. So pardon me if I gloss over things a little bit and go quickly, but otherwise we'll never get finished. I'm just keeping an eye on the time. You can see the actual executable there, a couple copies of it actually. I've gone ahead and pre-made an IDE file. And what this is a copy of the Trojan just after IDAPRO finished its initial auto-analysis. If you're an IDAPRO user, you may be familiar with the step that loads it up. It goes through and identifies all the pieces. The light blue are the library functions. The pink is the import table. The dark blue is your typical program code. The reason I didn't show this is it took 11 minutes on my laptop, which is quite a long time. It's not a particularly fast laptop, but that's a lot longer than this sort of thing normally takes. And I certainly didn't need any filler time for this talk. So I skipped that step. And again, as I mentioned, if you're not an IDAPRO user, it goes through, it's got some heuristics and some other tricks where it identifies the library calls, the programs, and a bunch of other pieces. The gray and the brown are typically data sections, or some other sort of thing that's tagged as data as opposed to executable code. There's immediately a couple problems that we have with this particular thing. First of all, okay, well here's the entry point, win main. And if you expand it, it doesn't actually have anything terribly interesting in it. So, okay, it's got a subfunction. Let's take a look at that and see what's below here. And again, the blue and the pink are kind of key visual indicators. This thing's all library calls. The black would normally indicate our program. And you can take a look and see this win main doesn't point, at least not directly as far as I was concerned, to any of our code. Second problem you'll see is that we have a lot of unidentified functions that appear to be getting called by library functions. This means that we've missed identification of some of the libraries. And in this particular code, as I'll demonstrate, this ends up being a huge problem, a real annoyance at least, with this particular program. In the interest of time, I'm going to skip how I found the entry point in detail. Suffice it to say that this is an AFX application. If you've done any Microsoft programming, this is kind of a cut-down version of the graphics libraries and a bunch of other stuff. Means it's done in C++, most likely, and sure enough, looking at the rest of the code, this program was done in lots and lots of C++. and I found the entry point at 407C62. I found out a couple different ways. One way you can do it is if you pick a random chunk of the blue code and then ask IDAPRO for the parent chain. Most of the functions all point to this one parent, which you would assume is the main function, and it turns out to be the case. The other way is that I trace through, manually disassemble a little bit of the AFX library code, and the way it works actually is it goes through a bunch of subcalls. It points to a structure inside the program, which is a list of functions, and apparently at offset 18 hex, because that's hard-coded, that's your original entry point. That's how I found it. So this is the main function, and again, as I mentioned, this program's huge. If you've got a smaller piece of code, sometimes it's nice to take a quick look at the structure and see, okay, can I find some functions at the bottom that would be nice things for me to target for easy, figure out what they are, and that's going to give me a lot of flow up. And in this case, the program structure is not terribly helpful. It's just too large. You can zoom in, obviously, and start seeing some of the individual functions, but there's just way too many to actually get much sense of this, so we're going to have to do this in smaller pieces. Two ways to go about exploring a program like this, or two easy ways I can think of. One is just look at the strings, and if you've got a nice unpacked program, you've got a good collection of strings going. So let's take a quick look through those. I see a lot of misidentified strings, a lot of system call and localization type functions. More system calls, library calls, I should say. I see a lot of GUI stuff, which is interesting for a Trojan. Usually they're trying to be a little bit stealthy, and there's a reason for that. Okay. Now we're starting to see some of the stuff in the actual program itself. So, okay, well, it looks like it's probably setting itself to run its startup. Pretty common. Okay, want something from Microsoft. Some executable names. And again, okay. Looks like this could possibly be a list of commands. Oftentimes with a backdoor Trojan type application, you'll see it checks into some sort of communication channel and waits for commands. So sometimes you'll see a big loop someplace that says, check if I got the command to ping people, check if I got the command to DDoS somebody. Okay, there's a couple of settings that I know from looking at this thing, and again, I'm cheating here. I spent quite a bit of time on this thing before the presentation to hopefully speed it up. These two settings are used for figuring out your Outlook Express email address and SMTP server. Other pieces that you'll find in here, if you look around a little bit, you'll find that it makes reference to a screen grabber. It makes reference to a keylogger. So there's some other pieces of the code where it's obviously grabbing a bunch of stuff off your system. This particular Trojan also will, upload files, download files. There's a bunch of different functions to it. You can look at the antivirus company's descriptions of it if you're interested. Almost all of them are calling it Hot World. So that one apparently was pretty universal when they started naming it. If you're curious, if you were to actually run this thing, it's going to show this graphic here. And it's going to sit there and let you try and type in passwords while it's installing itself, calling home, uploading files, all that kind of fun stuff. And this is the Trojan part where it says, I'm going to fool you into thinking that I'm something legitimate. It's not going to work, and of course they're going to fail and maybe mail the guy back and say, hey, I couldn't get that to work. And he's going to mail back and say, oh, sorry, well, here, try this one instead. Meanwhile, of course, they're already infected. He already knows that they've, run his Trojan. A couple ways I mentioned of, one way is looking at the strings and focusing on a function. I decided to try and find the phone home section of code. A couple different ways I was looking for this. I started to focus on the imports. Click Good? I'm in the wrong window, that's why. Okay. So here are all of the functions the thing loads. So you could look, for example, for the WinSock functions. WSA startup, I looked for those just to give you some idea how I found this. They weren't terribly interesting. I found two places where it calls WSA startup, one for WinSock 2, one for WinSock 101. Neither one of those were directly what I was looking for. It's got them wrapped in a function that calls them every single time and tries to talk on the network as a safety thing. So those weren't directly useful. What I did find, check my notes, was that it checks the internet connected state in a useful way. Yeah, just search for it. And in fact, there's only one place where it checks for that. So I previously determined that this is the phone home function. I'm going to put the mic down a little bit so I can type. So I found the function I want to focus on, and I want to show you a little bit of how I would go about marking up a function so that it's actually useful, readable, and I can actually start getting it into my head to see what it does. One of the very first things you want to do with the function is try and identify the endpoints. So here's where it returns. Oftentimes you don't know a lot of what's going on quite yet. So it's okay to go ahead and mark up labels with things you don't know. So I'm just going to call this call return ESI. My habit is to mark up the return functions, name it return underscore whatever value it's returning. If it's not returning anything, or it's not being set here, I just call it return. If it's returning 1, I'll call it return 0, return 1, returns register. A lot of functions will have a return variable, and they'll return that instead. If there's any loops in the program, you want to find and mark up those. I don't see any obvious ones. I'm looking on the side where the arrows are. You'll get a nice thick black line if it jumps upward, which oftentimes indicates a loop, not always. So I'm going to do a quick graph down from here. I'm running out of time. Try and figure out some of what this does. Okay. So this guy doesn't call too many children functions that aren't libraries, which is nice. Take a look at this guy. Okay, so here's one of the problems you get sometimes in C++ applications. If you're used to using idocro, normally these would all be variables. The problem is that idocro has not realized that this function uses EBP as the variable pointer. It's normally looking for a signature at the top that would tell it that, and in this case, being a C++ program, instead we've got an exception handler set up. The way you would do that, fix that, is you go to edit, function, and you would say BP-based frame. If you prefer to use the keyboard, Alt-PBK. There we go. And you can now see it's filled in arguments, functions. This is important because it'll start picking up variable names from the system calls that it makes. If it knows a particular parameter to a system call is named this, it'll assume that name if it's clear that your program is also using it in the same way. So we can see some of the functions in here, and again, you mark the return. And I'm running out of time. I'm going to have to move on to the next demo here. But some of the key pieces you want to do in terms of name your variables. If and when you can, go up and put in function prototypes. So down here, I've got arguments to this program. I've got at least one of them named. I could go up here, press Y, and start a function prototype. Now I've run into another problem with the fact that I'm using C++ here, which is most of the functions in this program are starting off with a structured exception handler setup routine, which throws off the stack. This throws off IDAPRO's stack analysis. So I've got this floating argument that if I try and set up a function prototype, it's going to end up screwing me up. Take a look here, right before the first function is an int, which is just kind of floating around. That's because these guys are normally supposed to start at 4. They're starting at 8 because of that structured exception handler screwed up my stack. I'm going to have to move on with the presentation here. We're real short on time. But I did find that this particular function will call home. It actually it calls do an internet connection, and it sets up by default trying to go to 443 SSL in HTTPS. So that's an example, and I apologize I didn't have a little bit more time to demonstrate that, of an unpacked executable. This is what you ideally would have, because when you get a program that's unpacked, you get all of your imports and all the other nice pieces that you want to see. Briefly to reiterate, especially since I didn't get to cover all of them, some of the naming conventions that I use that I find keep me on track and work for me are to do a bottom-up analysis, meaning you go through and find any return instructions. Those are places where your function exits. Mark those first, because then when you're going up and trying to figure out, okay, it calls this function, it checks the return value, it seems to be a 0 or 1, I don't know which one's success, I don't know which one's failure. Oh, well, guess what? This one goes straight to the return function, so that's probably my failure case. Whereas the other one goes straight down and does the rest of the function. Mark loops. The reason for those are when you're working on a function and there's a bunch of these labels which all initially say location and memory address. If you just mark something as a loop, and I go through and I mark them as loop 0, loop 1, loop 2, 3, I don't care initially what the loop does. That's one more label that you don't have to identify and worry about naming. Name your variables as quick as you can, even if you get it wrong initially. Oftentimes you'll find a scratch variable that you've named something because it's being used that way in a function, and later on you find that it's being used for something completely different. Well, it turns out to be a temp variable, but at least you've named it initially while you're working that portion of the program. Naming convention. By that I mean when you're tracing through a function and you've got an option and you run into a place where it jumps to another label. There's two things you could theoretically do there. One is name that label with how you got to it, i.e., okay, I just checked my internet connection status, I got success, I'm going to name that label that I'm going to internet success. That's actually easy, but that's not the most valuable way to do it. The reason being that there may be more than one part of the program that jumps to that label. So you want to try and name labels with what I call the from function. What below that label, what its function is, name it that. So if it turns out after internet connection success, it says try to FTP, name it try to FTP. I didn't get the chance to show me manually tracing through a function, I'm short on time, but I have a very strong tendency to comment almost every single line. Even really, really obvious stuff. If you get something like an XOR, EAX, which is assembly shortcut for setting EAX to 0, I will go and tag a comment and I'll write in EAX equals 0. The reason for that is later on, when I'm glancing up at the function, there's this nice blue comment that sticks out that tells me exactly what EAX is, and I don't have to figure it out again. So I try to comment every single line. I think these are some of the habits of people who have some experience doing disassembly. I talked with Nico about this a bit, and he tells me he does almost exactly the same sort of thing. So if you're a little bit of a beginner to it, I think some of these tips hopefully will be helpful. Again, moving on quickly, some of the barriers you find to do in disassembly. Packing and encrypting, which Nico's going to demonstrate. I haven't left a lot of time, but we're going to do our best to do a demonstration here. Higher level languages or object orientation. I just showed a bunch of places where C++ is causing us a little bit of grief. I didn't show it there in that particular example, I didn't have the time to, but that program uses the C-string libraries extensively, and unfortunately IDAPRO doesn't have a signature for those. So there were a good couple dozen C-string functions that I didn't know exactly what they were, so I was left guessing in a bunch of places. And it's really no fun reverse engineering a library call. They're complicated, and you feel like you wasted your time when you're done because, oh crap, this is just a string copy, or something like that. P-code. This actually comes up a fair bit with malicious code. You'll find a lot of it written in Visual Basic or Delphi, which are semi-interpreted languages. So you get a mixture of some compiled native code, some P-code. This is the internal language, and those can sometimes be a challenge. There's not a lot of really fantastic tools public for analyzing some of those things. I know most antivirus companies have private tools that they don't share, and you'll find a few if you go searching. And then self-modification is a bit of a pain in the butt too, where you go and figure out much of what a program does, only to find out later on that section gets overwritten by something else. IDAPRO in static mode doesn't have a great way to represent this, so that's one of the reasons why it's a pain. So the other Trojan I wanted to briefly show is, you may recall a week or two ago there was this flap about this Michael Jackson Trojan, and I got one of the emails. And I did some research. And the way it works is it sends you to a website. The website exploits Internet Explorer. I didn't identify the exploit. I don't think it was a 0-day, but I think it was. It downloads in a few stages. The ultimate piece that it ends up downloading is this scpr32b.exe. When you're looking at an executable, you can load it up in IDAPRO relatively safely. There have been a couple of exploitable problems in IDAPRO in the past, but I believe the current version, as far as we know, is safe. However, I'm in the habit of taking a glance at everything in Notepad. If you get used to looking at executables, you notice certain structures. This one immediately screams out UPX-packed to me, if you've ever looked at UPX-packed executable. Some of the key signs are, I've got nothing recognizable in the thing, no strings, and I don't see a big list of imported functions. Okay, so there's something funny going on there. I'm going to go ahead and run this utility called PEID on it, which is a packer identifier. And point it at that file. It's encrypted with a modified version of Yoda scripter 1.x, which is interesting because I thought it was UPX. There's some appearances there that make it look like UPX to me, some section names. But maybe this particular crypter is designed to look like UPX, maybe something else is going to go on. So at this point, you could load it up in IDAPRO. And IDAPRO is going to tell you a lot of the same thing, which is, something funny's going on here. This might be packed. Are you sure you want to load it up? You say sure. And you can tell pretty quickly that this isn't a normal program. Normal code doesn't jump around all like this, have things like the call one instruction ahead and things like that. So what you would normally do in this case is you have to have a way to unpack it. In my case, what I do is I call Nico.
I'm going to present B-files unpacking, and unpacking knowledge at the very end. Unpacking knowledge is very handy for reverse engineer because a lot of files are packed, especially malwares, and there are a lot of different packers and protectors. So sometimes worms or malwares are packed with custom packers, and tools like PID won't identify the packer. So a few tricks to find out which packer has been used, or if the file has been packed, is to look at the last section of the executable and look at the characteristic of the section. So if the last section is executable, maybe the file has been packed, or maybe it's a virus, sorry. we can have a look at the first section, and if the first section characteristic is writable, maybe there is a backer going to impact the first section, so you need to write access to it. We can have a look at the first section row size, and if the file has been backed, the physical size of the first section is new because it has been removed and backed in the last section. We can also have a look at the last section, at the entry point, sorry. And if the entry point is starting in the last section, it means that something has been added to the program. Because usually programs start in the first section. It can also be a virus. You can also check section names, and you can find something like UBX section names or ASPAC sections. So sometimes it gives you an idea of the backer being used. We can also check the import table, and if there is a very few imported functions, it might be because there is the backer import table and not the real program import table, so it might be backed. We can also check for strings. Usually backers are backing the data section where we find every string. So if you find no string at all, maybe the file is backed. Another hint is looking at the row size, and if the file has been backed, the physical size is going to be smaller than the virtual size. So you can see the entry point address here, and you can see that it's the last section virtual address. You can also see that the row size is new here, so this file most likely has been backed. Another example, if you look at the last section, the resource section here, you can see the characteristic, and the last section is executable. Resource section usually are not executable. So it might be a hint that the file has been backed. So now the basic unpacking method, you have to find the original entry point first, and this is the start of your impact program. So a few ways to find the original entry point is to trace slowly until you jump to the real program. You can also use a static disassembly and look for jump to the first section or hints to jump to the first section. Or you can use a live debugging and put smart hardware breakpoints. And you can also use API functions breakpoints, because compiled programs like C++ programs are going to use standard API functions at the entry point. So you can just put breakpoints on those functions and run the program and just look above if you are at the entry point. Once you have found the entry point, you have to dump the process to your hard drive, so you have an impact version of the program. And then you have to reconstruct the import table. So you have a few ways to do it. You can trace the backer and find where the import address table is being handled, and grab information or patch the backer so it doesn't redirect functions. Or if you are lazy, you can just use a nice tool called import reconstructor to reconstruct the import table automatically. So I'm going to do a demonstration.
I should have that item running. Set that back and forth.
So this is the program. The program is backed, and this is the backed entry point. I'm going to do it in live debugging, and hope I'm not going to be infected.
He's using my laptop for this demo course.
So the first thing is to start the program and stop it at the entry point. Okay, so the program is currently paused at the launch point of the back program, and I'm going to trace through the backer. One thing I usually do is to patch the one structure. When you start a program with a debugger, there is a structure called the PED, which has a debugging field, and it's set to 1 when you are debugging the program. So you can just patch it. So you can patch it to make it think there is no debugger at all. Oops, mistakes. I didn't. Okay, so now every function using this field to check whether we are debugging a program are going to think there is no debugger at all. So one thing I usually do is I usually put a breakpoint on the first section on write access, because backers are going to back the first section, and to do this they are going to write to it. And I don't want to trace through every instruction in the backer. So here we can see there are a few segments, and we can see UPX names into segments. So maybe this file has been backed twice, once with the decryptor and another time with UPX. So I don't want to put a breakpoint in the first section, because UPX is going to impact in this one. I will put breakpoints on the UPX section, on the write access. I will put two breakpoints just in case. This is not my computer. Okay, no, I'm just going to run the program and check it's writing to the first section, or the section where I need put breakpoints. So you can see this memory location has been accessed with write access. And we are right inside the backing loop. There is true access. So I can start tracing slowly. Because once the backing has been done, you usually have the import table handling functions, and then eventually you will find to jump to the original program. And then you can see the backer is checking about the function names. See the resource section, and is doing some checks on it. And I'm just lazy, I don't want to go there, so I bypass it and continue to trace. I usually scroll down a little to see what's going on, and I usually look for the import section, the handling. This constant is usually used for checking whether there is original function being called by original naming, and so this is a nice hint about the import address table handling function. So I can still scroll down. At some point, we are going to find some loop and encrypted code behind it. So it might be a nice point to stop at, because it's going to self-decrypt itself. So I can just put an hardware breakpoint on the loop. This time on execute access and run the program. It stopped. So now we just want to let it decrypt itself and continue to rush info. Here there is a call to an array function, it's checking whether we are debugging it. But since I patched the field when I started to debug it, it's going to find things there is no debugger at all. So I can just continue tracing through it. There is a few loops, and here we can see that the program is going to install an exception handler. Packers usually jump directly to the entry point, or they can use a register, jump to registers, or they can also put an exception handler and create an exception to jump to the original program. So it might be a nice thing to check out. It's putting in EAX the exception handling function. You can just put a breakpoint on it. And let's just run the program. So it's going to break on it. And here is a final jump to the original program. And to find the right address, we have to look at the instruction accessing the context structure. So here we can see that the program is going to access the context structure and is going to modify the EIP register, which is an instruction pointer. So we have to look at the value of this register, because this is going to be the next location where the program is going to jump. Right inside the UBX1 section. So you can put a breakpoint on it and just run the program. So we just passed the first packer, and now this is the second one. UBX is very simple, so we can just scroll down and try to locate to jump to the original entry point. At the end of the packer section, we can find a jump. It's most likely going to be the one jumping to impact program. So we just put a breakpoint on it and just continue trusting.
He's hitting the earlier breakpoint that he'd set when he just looked at the Yoda cryptic portion.
So we just stopped on the jump, and if we single step once, we are right inside the original program, and everything is back to memory. So now we can just make a memory dump of impact program. We are going to use import reconstructor because it's very nice too. It's a process dumper and an import reconstructor. So we just select your process. We have to put the right entry point here, which is 7444.
Yeah.
Press EIT auto search. So it's searching for the import table, and we can get the import. So we have every imported GLLs and function right here. So I'm going to make a dump of the process.
Overwrite.
And then just fix the import table. Job done. Everything is reconstructed, and now we can start statistical analysis. And we can close the library malware.
Thank you. Yeah, I didn't get on. Couple of quick points there. If you've used the import reconstructor before, you may be aware that it doesn't always leave a perfectly working executable immediately. You may have to do a little bit more work on that. Since this is a piece of malicious code, I'm perfectly okay with the fact that it may not actually run. Instead, what I'm interested in is it now easily analyzed in IDA Pro? So, as you've seen before, when I tried to load it up, I wasn't getting a very good dump. In fact, I was just looking at the cryptors code. What Nico found out was that this was, it looks like it was first packed with UPX and then had the Yoda cryptor run on it, so there's actually two. You may have each noticed the two different places where he set breakpoints and caught that. He's quite good. I mean, there's a reason why I got him to do this. He just did that in, I don't know what, 10 minutes, and it only took him a few minutes longer than that, and he did it for real for the first time yesterday. So I'm very lucky to have him to demonstrate to you the unpacking piece. If you notice in the original slides, there's a pretty lame discussion on how I used to do the unpacking, and replace those with this section. We've updated slides to the conference guys. You can download them out. All right, I'm a little bit over time. I'm going to try and go through this quickly so you guys can get lunch here. I'm loading up the now unpacked executable, and let me get rid of the hot world too while I'm here. Yeah, I'm going to overwrite the one I've done before. Didn't complain about the imports table that time. That's a good sign. And you see you actually have what looks like a real win main, and IDAPRO's finding lots and lots of executable code. So again, apologies, this is going to take a moment. Okay, so it's going through. I'm going to see if I can see the structure at all yet. This is still quite busy, but it's far, far better than the Hot World one in terms of what we're looking at. So this is this case where the structure is actually usable. So you could go through and find some of the bottom functions and things like that. In this case, the quickest way, and again I know this because I cheated, I looked at this before, the quickest way to get to the answer on this particular one is the create thread call. So if you go to the imports section, look for create thread, and this is one of the reasons why IDAPRO is, oops, I got the wrong one. So there we go. Why IDAPRO is really nice is you get cross-referencing names and everything. So I'm going to look at a couple of the create threads real quick. It'll generically name them start address, which is not terribly useful. But if I go and look at one of these, okay. And again, I'm trying to be quick about this. Okay. I've got a DNS name I'm looking at, members.metabond.com, as well as web.megadon and a bunch of other host names. This is kind of an interesting Trojan, by the way. This is starting to be a trend with the Trojans, in case you're curious. These names don't exist yet. They may not ever exist. However, if you get yourself infected with this, it can't call home for updates yet. It can't hit the IRC servers yet. However, the guy who wrote this probably owns those domains and can turn them on in the future. And all of a sudden, his bot army checks home and is able to receive commands. This is starting to be a trend where people will prepare a domain or host name to be a control point later on, but it doesn't exist yet. So you may think that it's been shut down. It may not have actually been started up yet. So I'm just glancing through here. Okay. So ping and pong. What section of code am I in? What does this piece do? IRC client. So I'm going to mark this guy IRC client. And if you take a look at the code, so this entire section of code I can assume is related to the IRC client. Let me go back to the create thread. I'm going to go to the next one. See anything obviously identifying yet on that one. We go to the next one. The thread that it's going to is this guy. Socket call, bind. Now, this isn't calling bind or socket, it's actually using the words. This tells me I've got some sort of proxy encode. So we'll just call that proxy. And look at the next one. Similar things. So I can see some of the variables are getting filled in with strings, unknown, bind, UDP map. I'm looking for some more identifying strings here. Bind, get sock name, HTNS. Okay. So I start playing with file descriptors. This is indicative of a piece of code that is managing 100 sockets or something, rather than a single one. So this tells me maybe I've got some sort of DDoS code, or a multi-threaded proxy, or an IRC bouncer, or something like that. So I'm going to call this thread proxy2, maybe DDoS. And short answer is those are some of the main functions of this particular Trojan. This one's actually quite a bit friendlier. It ends up being a lot smaller when you're done. The dump is 114K. The library functions were well identified. I forgot to mention it on the other ones. One of the things that you'll see typically is that all of the library functions, the light blue, tend to be, doesn't have to be, but tend to be in one huge chunk. So if you've stepped into some code that looks very confusing to you and you write surrounded by two chunks of blue, light blue, but you're looking at something that's not been marked, you probably got an unidentified library function. Something to keep in mind. Okay. Okay. I apologize for over time. We had to go really quick. I think we kind of way underestimated how much time we would need to do this properly, but I appreciate your patience. Briefly, before we let you go to lunch, do we have any questions? You have choice between asking questions or reading. Okay. If not, then